Shah, and I told him I'd plug his book. He didn't want me to, but it's Web Hacking Attacks and Defense. Breakpoint's got it outside. He'll be doing a signing at lunch. You doing it upstairs at lunch? Or?
Somewhere.
So look for him, pick up a copy if you don't have it. And Mr. Shah.
I will refrain from using this haunted house mic because it's making all the creaking noises. Scares me. As if the audience doesn't scare me even further. Thank you, Arthur. Thanks for the quick introduction. I will just add a little bit more to it. I am Saumil Shah, director of NetSquare. We are a little sharp security shop based out of India. But we've been here, we've been working in the US and stay on top of HTTP research. That's our game. I would be failing in my duties if I also did not point out the help of my colleague Sriraj, sitting in the first row, another co-author of Web Hacking Attacks and Defense. He is the silent but deadly types. He does a lot of research, and together, what we've worked on and what we're going to bring to you today is all our efforts put together. So with that, hope you enjoy the talk. What I'm going to talk about is some innovations in the way we do web security, and three key concepts that I'm going to talk about, and I shall introduce them as we go along. As usual, please feel free to pound me with questions once I'm done at the end of the talk. If the question is entirely urgent, you may feel free to stop me even in the middle of my talk. So let's go. So before we begin, I always introduce this little slide so we get an idea of what our playground is. This is what I call the web hacker's playground. This diagram has been borrowed and beaten and reproduced in many, many places, not copyrighted, so you can use it as well. So what do we have here? On the left-hand side, we have the web client. That's our web browser. And everything to the right-hand side is the web application area. You typically have a firewall, which is pretty restrictive, allows only HTTP going in and HTTP coming out. There's a web server, which catches most of the front-end requests and serves you the static pages and stuff. But for a complex web application, you usually have web application servers plugging in, either running in the same memory space on the same computer, or they're on different computers. They're connected via some plug-in mechanisms and such. These will typically have the entire business logic of the application hosted on them. The front-end web server does the input gathering via forms and renders the output into HTML, etc. And usually these back-end application servers are powered by databases. And there's an SQL connection with the back-end database. So this is the typical layout, and this is what we as web hackers will be focusing on. So this next slide is something like what has been the evolution of web hacking since the early, the late 90s. Everybody was concerned with firewalls, RPC, buffer overflows, Windows, NetBIOS stuff, and whatnot. But the web hacking was still an esoteric area. I think, if I can recall, things began with the classic PHF bug, where you could extend the PHF and put an ampersand, xterm, and such, and get xterms thrown back to you. Then slowly came along automated web vulnerability checking. A notable achievement was done by Rainforest Puppy with Whisker. So he's looking for web vulns all over with multiple get and head requests. And then came the whole game of input validation attacks, which is not so much automated. It's you look through a form, you find that there's some parameters that you can tamper with, and you poison the parameters, get the app to blow up or throw back connections at you or whatnot. Then there's the game of buffer overflows, either in the web server or the app server, or even in the input fields of the application. EI did some work on the IIS buffer overflow games and whatnot. Then came the whole arena of source code disclosure, where you have applications written in scripted languages like PHP or ASP, Java server pages, and you take advantage of a few flaws, and you get the server to return you the code in an unparsed manner. Some more advanced HTTP attacks are session hijacking, where you can take over, copy and paste some cookies and take over somebody else's sessions. Then, pardon me for using the word lame, but I coming from the server side, consider client-side attacks not as my area. So then there are, the whole cross-site question mark type of attacks, where you get JavaScripts popping up on everybody and stealing cookies and whatnot, hacking grandma over AOL. So this is, how far things have come, and what is it that lies next is what we're going to talk about. As far as the defense side goes, not much effort has been put into web defense as compared to the effort put into normal network and protocol defense. So we have, some of the defense areas are lock down your web server configuration as much as you can, make it tight. You can have web server plugin filters like URL scan or secure IIS, whatever have you, to do some sort of checking and filtering. Then of course, secure coding, who does that? It's a mystery, it's a myth. But I still preach that. Somebody asked me, what's the patch to input validation problem? There's no patch, it's called secure coding. And then, of course, one other thing for web defense is security by obscurity. You disguise servers and keep the script kiddies away. But how far all this is going to help us? Well, we'll take a look at it. So let me just talk about security by obscurity, first of all. In a lot of cases, I ask people, who's running IIS? No, not me, not me. People change the IIS server banners to Apache or Netscape, and hopefully they'll keep away all the IIS attacks away. If you change the Apache banner to something else, you keep the Apache attacks away. At least from the script kiddies or the automated things angle. A lot of cases, whenever an attacker is trying to focus on which server to attack or which server to analyze, when it comes to identifying web servers, we do not have many alternatives but to just look at the server banner. Yesterday, Jeremiah talked to you about web server fingerprinting, where I'm going to take that concept and build up some more, give you another parallel view of web server fingerprinting from my angle. So if we want to change the server banner, what are some of the common things that people have done? You patch the web server binaries. Say you patch the w3 svc.dll to change Microsoft IIS 5.0 to Apache 1.3.26. If you have the source, you can recompile. Say you have I knew a company that had Apache 1.3.26 and they recompiled it with a WebStar 4.2 server banner to keep people away. It works very well in defeating certain automated attacks or script kiddies, but we are not afraid of script kiddies, right? Nobody is. So, well, let's see what we can do then. And then there are other products. One of them, I think Jeremiah mentioned that yesterday, it's called Server Mask. Products such as these go a step further than just obfuscating the banner. Not only do they give you a different banner, they will also mimic the header of a particular web server. For example, Apache, they change the date and the server field order the other way around. IIS has it different. IIS has server and date. These guys have date and server. So it tries to mimic the other server as far as possible, and provides you better security by obscurity than just changing the banners. So this is as far as things have come. So now what I'm going to talk to you about is HTTP fingerprinting. What is the objective of HTTP fingerprinting is to accurately determine the underlying web server platform, independent of any banner strings or any response codes whatsoever. We can also take it further to as an attempt to uncover any plugins or application servers that might be fitted in to the front-end web server. And the whole theory is based upon what people assume when implementing HTTP specs. It's like some areas the HTTP spec is not very well defined. So what Microsoft's response to a particular request may not be the same as Apache's response and vice versa. It's pretty much the same as OS fingerprinting. Some areas of the IP protocol stack, as far as responses, are not well defined. And that is why people use it and are successful in identifying operating systems. So what are the kind of approaches to fingerprinting? There's classical decision tree based methods, saying it's more like a chemistry test. You know, if you add some acid to a compound, if it turns red, it's this. If it turns blue, it's this. So you have one test, you have a decision tree which keeps on going further, and then you decide more tests based upon which direction the tree takes, and then you narrow down and lock down your result accurately. Or you can have statistical or neural network based methods. It's pretty much what I've been trying to do. Is one is not dependent upon pattern matching or tree logic or focusing on particular tests, because servers keep on evolving and I can't keep track of all servers and all peculiarities. So what I do is I build a learning system. You just set it in a free learning mode, gathers all signatures, and you manually assist and classify them. This looks like IIS, this looks like Apache, because you know them. So once you train the machine, and it just keeps going and keeps improving its weight vectors. So the fingerprinting engine, one usually, if you're based on a decision tree based method, you have a set of test cases which are carefully chosen in a response tree. Or if you have a statistical engine, you have weight vectors. Neural machine, you have weight vectors which just keep on getting refined the more you train it. What are some of the techniques that are used? We detect, we'd usually like to focus on what are the deviations from the HTTP RFCs. If the RFC says something and you get a different response, then these are the kind of peculiarities. So you have a set of tests, you throw it at it, see what peculiarities you get back, and then the machine learns from there. The behavior sometimes is not specified by the HTTP RFCs. Should I give a forbidden, or should I give a not found, or should I give a 500 error? So sometimes developers just figure out, this is the best way I'm going to respond to this kind of an error scenario. Sometimes things like the header field order matters. Error analysis, what responses create what type of errors. Sometimes you even have cookie strings, like Microsoft servers will return an ASP session ID, or Apache servers will return the IP address and some other strings with it. If you know these cookies are generated by a particular flavor of server, you can detect that as well. Products like server mask even go so far as to obfuscate the ASP session ID. But that's not going to stop us in fingerprinting, as you shall soon see. So the whole approach is pretty much similar to OS fingerprinting. What are we really trying to achieve through fingerprinting is accuracy. The accuracy of your results is going to depend on the choice of test cases. In that matter, I would vote for a statistical machine as opposed to a decision tree based machine, because decision trees are hard to scale. And then, of course, a lot of accuracy depends on the kind of scoring system that you've implemented. You justify the weights that you've picked. And you need a very good training input set to train the machine. Once it's trained, it's all right. You just can't set it in the wild and let it learn. One of the biggest problems with HTTP analysis is, as far as a protocol goes, HTTP is very easy to customize. You can change banner strings. You can write your own modifications or plugins to change response codes. So you really, if you want to do accurate analysis, you can't depend on 200 OK or 404 or such. But there are ways of getting around that. So let me give you 3 examples, and I'll go into a demo and show these in front of you. Here is the first example of a little prototype that I've built. In this screenshot, we have the server reporting itself as Apache Advanced Extranet Server 1.3.19. This is the string that you get from a GET or a HEAD request. And then the fingerprinting engine compares it with known weight vectors for IIS 4.0, 5.0, 5.1. Here you notice it will take each weight vector and give a score. Say 23 is the best it could do for 4.0. 23 is the best it could do for 5.0. As far as the Apache groups go, the scores are higher, 70, 77, 76. Apache 1.3.x scores 78, and that happens to be the highest score out of any weight. So the engine says, the best match seems to be Apache 1.3.x. So this is how we do the differentiation, based on the highest score wins theory. In this instance, there is no obfuscation. It's just a verification of, it's just a verification that the engine works perfectly well. In this instance, we have a server which reports its string as web star, but in reality, what is it? It's an Apache 1.3.27 or 1.3.26 server. Somebody just recompiled the source of Apache and changed the server banner to web star. And again, you see that as if we look at the scores, the two Apache weight vectors score the highest total. It's fairly easy to tell of such trivial obfuscations. There's some advanced obfuscations. For example, here's a server running with server mask 2.0. It's an IIS-4 server, but the string comes back as Apache 1.3.23. Even the field orders come out in an Apache fashion, but that really doesn't defeat the fingerprinting engine. IIS-4 scores 63, the other IISs score 53, 54, and so on, and the best score wins. So this is a little prelude to fingerprinting. I think I'll be best able to illustrate with a demo. So let's get into the demo. Is this very legible to everybody at the back? Okay, great. So let me just make sure. I'll first of all open a browser. Enter the browser. There's a system I have called Red October. I installed Red Hat Linux in October. That's how I picked the name. But this is actually a basic static web page, pretty much like anything representative of the front page of Google or Yahoo. Doesn't have too much dynamic content. And we're going to use this as a control system to verify if things really work or not. So I have HTTP fingerprint is my program. I give it Red October as the target. And actually, let me do a netcat before I do that. Just show you the raw string. Netcat Red October port 80, head HTTP 1.0. And we have the string returned as Apache Advanced Extranet Server. No obfuscation done on this. So let's run HTTP fingerprint against that. HTTP fingerprint Red October. It first of all, where's the mouse? Yeah. It first of all pulls up the header, as I showed you in netcat, and then it goes on to reporting each score. So it showed it showed the best match as Apache 1.3.x, and below it you see all the totals that are returned. The IIS scored 32, 40, 43, etc. Apache 1.3.x scored 92. The other two, .27, .26 were close behind with 90 and 91. So this is a verification of the whole fingerprint. Now, let us take a slightly different example. We have, there's another server which we have, 19. Yes. I beg your pardon? Should I do the netcat thing again? Okay, not a problem. All right, so we'll just do the netcat thing again. We have Red October is the IP address, the host name, port 80. We do head HTTP 1.0, and this is the HTTP header that's returned. Don't worry, we'll revisit this many times as we go along. So this clears up your query. This is not obfuscated. This is zero obfuscation performed. Here's another server. Here's an IIS server which does not have any obfuscation, which is 192.168.7.247. So here's a web page for this server. It's just 2 HTML lines. And let us run netcat again and verify this, what it is. So netcat 192.168.7.247, port 80. Again, the same request, head HTTP 1.0. And the server banner comes back as IIS 5.0, and the other peripheral server header strings that IIS returns. Now, let's run the fingerprinting engine against this and see how it fares. So we have HTTP fingerprint 192.168.7.247. So we have the string pulled up, and in a little bit it pulls up best matches IIS 5.0. You see the IIS 5.0 scored 131 amongst all the other servers, and the Apache scored low in this area. This thing even detects IIS running with URL scan. So as many different servers as you train it against, it will easily learn and begin detecting the same. It does not. I do not have to alter any assessment logic. Number of requests remain constant, and the computation time remains constant as well. It could be further optimized by some decision tree based method, but for now I worked too hard to bring you all this. So maybe next Black Hat you'll see optimizations in this theory. So this is running it against non-obfuscated servers. Now let's put it to the test against some obfuscated servers. I have another system over here, which is netcat 192.168.7.248. Let me just show you in the browser first. 248. And well, here's some website of a electronic shopping store kind of a thing, sells art on the web. But if we launch a netcat request to port 80, say head HTTP 1.0, it returns back saying server is Netscape Enterprise 6.0. It seems to be fairly hardened because now you don't have other peripheral e-tag or content or anything else being returned in the header. Just the minimal headers that are needed to serve a web page are given out. So now let's run the fingerprinting engine against this. HTTP fingerprint 192.168.7.248. It pulls up the header, and let's see who won. The best match is Apache 1.3.x, and it's really an Apache 1.3.x server. It wins with a score of 55. It was an Apache recompiled with Netscape 6.0 as a server string. So yeah, the engine will detect all these anomalies and report them back. And now let's put this to an even further test. We're going to go back to that IIS server and run server mask on it and see how that happens. So let me just pull up that screen for you. Here is the server. Here is server. Oops. Bloody hell. Thanks, Windows. It's interesting. This is Arthur mentioned, what are you doing with a Mac in a Windows security conference? But oh well, maybe we'll have a Black Hat Macintosh someday. Cancel. Please. Will server mask never run for me? Wait a second. I did my prayers all right, I assure you of that, to the demo gods, but apparently they're not happy. It's screwing up. 1 second. Give me some time with this. All right, I will do one thing. I will give you the server mask demo a little bit later. Just give me a second to restart this thing. Okay, we will revisit this. I've just restarted the VM engine, so hopefully we'll be able to do this before the end of my talk. Let's get back to the example. But what I wanted to convey across is how statistical fingerprinting works. The demo with server mask is pretty killer because no matter even if it's activated, the fingerprinting engine still comes back and says, this is an IIS server. So my whole theme is, you can't really trust security by obscurity when it comes to focused attacks. So let me go ahead. So we saw this, and now let me talk to you about an entirely different concept. The concept I want to talk to you about is called page signatures. It's a little bit difficult to grasp than HTTP fingerprinting, but first I'll describe you the problem, what we're up against, and then how can page signatures really help us. So usually what happens is when you do web assessment, like say when you run Whisker, what does Whisker really look for when saying yes, a vulnerability exists or no? It usually, the first thing that it looks for is the HTTP response code. If you have a 200 OK, means that the resource was there. If it was a script, it executed and such. And you get the response code back, and then you say if this thing existed or not. But in a lot of cases, people have customized error pages. It's very easy to write a little program that will return you customized response. So instead of a non-existent page being returned, 404, you get a 200 OK. But the screen shows, oops, your page was not found. Here, you're penalized with 5 banner ads to look at, and some 20 JavaScript pop-ups that will make some exit control guys some money. So you have customized errors like that. Sometimes they say page not found, but they'll return you a 301 or a 302 to take you back to the starting page and such. Some sites have a 200 OK deliberately to fool crawling engines. The first page will contain a clear pixel, which will be linked to a non-existent link, and the non-existent link will return a 200 OK and 20 random links on the same page, which will all return 200 OKs and whatnot. So the crawler will get stuck ad infinitum and never be able to figure out your website. So this is what we're up against. So we can't really depend on the response codes So what do we have to increase our accuracy? We have page signatures. And the objective of page signatures is to accurately identify proper HTTP response codes. Even if it's a 200 OK, can we tell if it's a page which is returned as resource not existent and such? The idea is to minimize false positives. It greatly helps in automated testing because now you can say with confidence what your tests came back with. And this concept is not just to detect error responses or such. It can be used way beyond error detection. Like if you crawl a website and you get the same page signature for 20 pages, you can infer that these pages are driven off some template-based resource. So you can start grouping various resources together and form functional areas for your application and security analysis. Page signatures can be used in even funkier stuff, which I'll talk about near the end of my show. So here's what a page signature looks like. Each HTTP response in the HTTP header and the HTML data goes into computing this magic page signature. It is independent of the content in there, which is very important because we can't really trust the content being returned. It has the ability to overlook random contents. You can have random strings in there which keep on changing, but the page signature is impervious to any randomized stuff. The signature itself is a string of constant length, as shown in the blue box at the bottom. For algorithmic purposes, the computation time is order of n, where n being the number of bytes of the response. But the comparison time, because it's a string of constant length, is an order of k. So once you have the page signatures, working with them is very, very fast. There were other theories that had hatched in the past, to overcome this problem, but they were all order of n square, n log n time, and they never scale. We can't live with that. So here's some examples, and then I'll get into a demo, and hopefully the demo gods will not be mad at me this time. Here's an example of a normal error page. If you type in some HTTP site/garbage.txt, you get page not found. Here the requested URL /junk was not found. And if you do a netcat request and do the thing, it'll say HTTP 1.1 404 not found. In the next example, I have a customized error page, which returns some random number saying, this is to just simulate some randomized content which will keep on changing. Say, please contact the site administrator, blah, blah, blah. In 1 minute, you'll be refreshed to the main page, or you can search for your missing page with Google. And if you do a netcat, it'll say HTTP 1.1 200 OK, and then proceed to give you the content. This is very much like a normal web page response. To the browser, when we're looking at it visually, the user knows that this is an error page. But to an automated program, it's not an error. It's a genuine response. So with this, let me just give you a little demo once again. Pop open the browser. There's a browser. First, let's use the same control page, which does not have customized error strings. We go to Red October. This is the normal page. Let's make some request which doesn't exist. And it says not found. Let's try the same thing with netcat. Netcat Red October port 80 get / blah blah blah. Says HTTP 404 not found, and this is good enough because this is genuine. This is all you need to look at, and you can pretty much ignore the rest of the stuff and say this is a non-existent page. Now let us look at another server which is configured otherwise. 192.168.7.248, and let's try some error strings here. I say, oops, this is visually it looks like an error page. It has a random number. It says in 1 minute you'll be refreshed to the page, whatever. And now let's send a netcat request let's send a netcat request, say get / blah 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 HTTP 1.0. See, here we get a 200 OK. Here we get a random number and other such things. If I keep on reloading this, if I say reload, notice the random number is going to keep on changing. This is just one instance of a randomized field. There can be more instances of this along. I just cooked up a trivial demo to illustrate the fact. So now, let's see how page signatures can help us over here. I'll show you first the page signature program. It's page signature, HTTP. Let's try this for Red October. Just give the URL, hit enter. It gives us a constant length hex encoded signature. And this will remain the same no matter what. If I try page signature for some non-existent link, it will give me a different signature. And this will remain constant. Because the content remains constant. Now let's try the page signatures for that customized site. So we say HTTP 192.168.7.248, blah, blah, blah. Here we get this as the page signature. Where's the mouse gone? There it is. Now, even if we change something over here, or we keep on, say, hitting reload, which is giving the same thing, notice that the page signature will never change. So now, I know this is a response for a non-existent page, and this is going to be constant all throughout, as long as the site doesn't change. So if I know this when I'm doing my assessment, for every page that I come across, I get this signature, throw it away. This is a false response. Don't even attempt crawling it. Don't even attempt reporting it. Interesting. Let me show you what will happen if I run Whisker against this site. So I have whisker.pl and sh 192.168.7.248. Oops. There. It's running its Netscape Enterprise and reporting every vulnerability under the sun exists on this server. And something can't be right, correct? So now, let's say if I've written a script which incorporates, which is pretty much like a Whisker type testing engine, but with page signatures in there. And let me show you how that is going to fare against this site. Again, one does not need to have any prior knowledge about how the site is configured. So I have Whisker with page signatures 192.168.7.248. This is going to try for many, many checks. It's going to return the page signature for each check. But notice, for test.cgi over here, it returned a different signature. For, say, guestbook.pl, it returned a different signature. So now, if we know this, what we're going to do next, once this thing finishes, is do some more Unix magic. So now I know that this is a worthless page. This really does not exist. So I cut this. I do pipe to grep -v. Paste this over here. So filter out all non-existent pages. And the same thing will run, but it will only report me the genuine resources which exist. Like, for example, test.cgi exists. So all of a sudden, your vulnerability assessment has become deadly accurate. And this, we can manually verify this with the browser, and it will come back and show you. Another interesting thing to notice is take a look at the signatures for test.cgi and nph test.cgi. The signatures are the same because the output returned by these two is the same. So now if you have multiple pages like this, you can figure out are they came all from the same source or they belong in the same group. So let's just take a look at some of these test CGIs manually. Let's first say CGI bin. Yeah, there was one test which was perl.exe, which Whisker reported as existing, but it doesn't exist. So if you have perl.exe, it's going to come back with the error page. But if we have, say, test-cgi, this actually exists. If we have, say, nph test CGI, this also exists. It's similar. There was one marked difference. One was, can you see the little difference in there? Odd type and such. But the page signature is impervious to this thing. It really doesn't matter if the content changes a little bit. The base essence is the same, and therefore the page signatures are the same for these two resources. So for a web security auditor, it's very easy to just look at page signatures along with the crawled results. You can start grouping things. You can separate the fluff from the, I forgot that proverb, please excuse me. The wheat from the chaff, that's right. This is where they can come in useful. What else did I have to show you about page signatures? Should we try that fingerprinting thing again? I'm keeping my fingers crossed. Because after page signatures, I want to go on to proxy servers and tricks with proxies, and then I will end the talk. So let's revisit that. Let's revisit the server mask demo. I hope it works this time. All right, it worked. Whew. Okay, so we have server mask. We're going to enable server mask. We're going to disguise this IIS server as Apache, emulate the Apache header, remove the web dav, blah, 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 mask the session cookies. Yeah, everything's on. Apply, restart. It's successfully restarted. Now, away you go. Away you go as well. And now let's just test this once again with netcat and show you what it comes back with. Head HTTP 1.0. You see it comes back with Apache 1.3.19. The date and server fields are interchanged like a true blue Apache server is, etc. It really doesn't matter if these fields are there or not. My technology is impervious to it. And now let's run HTTP fingerprint 192.168.7.247. And what do we have here? It's IIS 5.0. Server mask is unmasked. And the scores in the last time without server mask, the score was 131. The scores just dropped to 111, but it's still the highest score. It's very easy to see that these two have the highest score amongst everybody else. So security by obscurity is defeated once again. Anyway, that was the demo for server mask. I finished the demos for page signatures. So now let's get back to the show. I'll wrap up page signatures a little bit. I will then go on to tricks with proxy servers. So just to recap a little bit, I showed you that page signatures are independent of the content. No matter if you have different URLs, if they're all of the same property, the page signature is going to remain the same. So here, all these are non-existent pages. Even if there's differences in the content is random, the response code is 200, whatever, the signature is going to remain the same. So now let's get to proxy servers and certain funky things. Let's try to apply the concepts we learned from page signatures and apply them to proxy servers and see how this can help us go even further. We all know what can go wrong with proxy servers. Sometimes servers can inadvertently behave as open proxies, allowing somebody else to surf the web and launch attacks from your site. And sometimes what is worse is servers can work as reverse proxies. That is, if you have a system which is dual homed and a web server running on that system, you connect to the front-end web server from the internet and you use that as a proxy to get into the internal non-routable network. In many instances, Sriraj and I have taken apart sites by just setting that front-end web server as our proxy and then saying go to 10.0.1.1, 10.0.1.2, and all of a sudden you're taking all their internal systems apart. What are the causes of misconfiguration? What are the causes? Why would web servers behave like reverse proxies? Especially, the answer lies over here, to go to this front side. Especially if the method to plug in web applications is fairly complex. There's ways like URL mapping or port redirection or things like that. This front-end web server will start proxying things to the back end. And if the configuration is not very well locked down, we have a problem on our hands. It can either be an open proxy or a reverse proxy. So sometimes devices or specialized servers like Compaq Insight Manager would act as an open proxy or a reverse proxy. Compaq Insight Manager, I think, has been beaten way too much, right, by people like poor thing, suffered from file retrievals to buffer overflows to reverse and open proxies. Anyway, so here's an example of what happens is you have a front-end web server which is dual homed. You have one routable or internet accessible address. In the demo it's not, because it's all I have. And you have an internal address and there's some other server sitting on the inside which this whole system works together. And if this thing is misconfigured or it acts as a reverse proxy, I can send a GET request like this, get http / 10.0.1.2 http 1.0. So this is actually a valid HTTP proxy request. It goes to here, this guy passes the request onto this internal server, gets a response and returns it back. This is how reverse proxies work. So now we can do many things with a reverse. For example, you can do port scanning through a proxy. All you got to do is issue multiple GET requests with different ports, so you'll find out what ports are open on systems inside. You may not get a valid HTTP response, but as long as you don't get a denied response, you're okay. And how do we figure out what response is valid? We just learned page signatures 15 minutes ago. So you send a request to port 0, you get no way to connect, take the page signature, and start sending these requests, port 21, port 25, and if the signature is different, then those ports are open. So here is how you can take one simple concept and extend theories far and wide. The only problem with trying to port scan behind a proxy is you have to somehow guess the internal IP addressing range. And sometimes it is leaked out through HTTP headers or through application error messages saying SQL ODBC error at 10.0.0.3. Brilliant. I now know what your inside range is. And computers are great at doing things automatically. So I set a large internal class C, have it running overnight. In the morning, I have my results. So, okay, I will again break for a demo over here. So let's see what we can do with proxies. So again, we will use the same system, Red October, as our control system. Think of Red October as Google. It's not going to change. It's accessible from all over the internet. So we will do netcat to Red October port 80, do a plain GET request, HTTP 1.0, and we get a response. Now, we have a server over here which has a proxy issue, 192.168.7.248, port 8001. here's a proxy server running which also acts as an open and reverse proxy. So with this, let us try to get the same page from Red October, HTTP Red October HTTP 1.0. So we're sending a proxy request to 192.168.7.248, port 8001, to fetch a page from that Red October system. And it does it. It gets you the same page. So this means this is an open proxy that we have. Now, this is a manual check. We can go to a web browser, set this as our proxy, and surf to Red October and find out the same for ourselves. So the question is, how can we do it in an automated manner? And for that, I have another script or a program based on page signatures. I have a program called proxy detect, and all I have to do is give it a potential candidate which might be a reverse proxy. And I've hard-coded it to look up Red October. I could hard-code it to look up Google and verify. So I suspect that 192.168.7.248, port 8001, is an open proxy. So I'm going to just give this parameter to proxy detect, and says open proxy detector. Via proxy, it returned this page signature, and directly, it also returned the same page signature. So we take the content, compare the signatures, and say, this is an open proxy. Let us take port 80 on this server and see if this is an open proxy or not. And it says, via proxy, it got this signature. Direct, it got this different signature. No, this web server on port 80 is not an open proxy. So now we have a very accurate, automated way of figuring out open proxies. Now, let's go ahead and try to pull up something like port scanning through proxies. Now I know that the internal, this 192.168.7.248 is a dual home system. On the internal IP addressing range, it has 10.0.1.x, that is a subnet. We can always throw the entire non-routable range at it to figure out if this is there or not. But for our demo purposes, I've just shortened it. So I have another program here called proxy scan 192.168.7.248, port 8001. This is my suspect. Once I figure out this is an open proxy, now I have to give it the range that I think is on the inside. So from 10.0.1.1 to 10.0.1.5. Let's just say I want to take the first 5 systems and look for open port 80 on these internal systems. So I hit this, say run, and it starts returning me results. 10.0.1.1, it came back with Netscape Enterprise 6.0. This is the same system which is dual home. The 192.168.7.248 and 10.0.1.1 is the same system. There's another system on the inside which is running Apache 1.3.19. This is actually accessible through the proxy. And we can verify this through a browser. Let's first verify it through Netcat. Netcat 192.168.7.248, port 8001. Is get HTTP 10.0.1.2, port 80, HTTP 1.0. It says object not found, returns you a server. So yes, indeed, this is how you can target other systems on the internal network through an open proxy. We can verify the same thing through a browser. What I'm going to do is set the proxy preferences. Network proxies. And oops, sorry, you're not supposed to see these. Sorry, those are my test proxies. Can't let you have that now, can I? So I enable the web proxy 192.168.7.248 port 8001. Say apply now. And go over here. Now I can start accessing systems on the 10.0.1.2 range. Yep, it does exist. Of course, no website is configured at this address, but yeah, we can start accessing systems on the internal network. So that's what I wanted to show. And like one last trick that I have to disclose. Before that, let me turn this proxy stuff off. I'm sorry? Yes. What he said is the way to scan internal systems is the same when it comes to ports 135 and such. Yes, that is correct. I'm going to show you that. So let's do that. All we have to do is just use the same program. Let us say proxy scan. Now instead of port 80, let's say 135. First IP address didn't have it. Second, it's actually timing out, or it's just not returning the connection back. But let me show you in another way. There's actually port 5800 open, which is VNC. Let's try to scan systems for VNC. So over here, yes, you do get port 5800 open on 10.01.2. Now, just one more thing. I'll go back to the demo. To the slides. Not only can you issue GET requests, you can also do HTTP connect, which is even more dangerous because connect frees you from the rest of HTTP protocol. All it does is open up a bi-directional TCP stream, and then you can tunnel whatever else you want over HTTP connect. It was originally meant to serve as a fix for proxying SSL traffic through, because SSL will just replace the rest of the HTTP. But in a lot of cases, if you have an open proxy or a reverse proxy, chances are you'll have HTTP connect available as well to reach any port. So now what you can do is establish a connect between a port on the internal system and then start tunneling all your data through. How many of you are familiar with this tool called data pipe? It's a port redirector. You open a local port and you forward the port to a port on the remote system. So what I did is I hacked up data pipe and put in HTTP proxy features through HTTP connect. So I'm going to give you a demo of that. Let me get back to this demo. We know that VNC is running on the system inside on 10.0.1.2. VNC runs on port 5800 through the web and 5900 through the native RFB protocol. So what I want to do is open up port 5900 on my local system. My remote host is going to be 10.0.1.2. The remote port is going to be 5900 on that system. My proxy host is going to be 192.168.7.248, and my proxy port is 8001. So now, this is the way I can use an HTTP proxy to connect to an internal VNC. So I run this. I'm going to do an ngrep to show you the traffic that really goes across. So now I'm going to open up VNC and connect to. I'm going to open up VNC and connect to localhost. Port 5900 is implied. Let's say I know the password. Notice all this stuff is happening. Let me show you what's really happened. Notice the connect went through. This is part of the data pipe. Whenever it gets a connection, it will shoot a connect, establish the connection, and then hand over the connection to the bidirectional stream that's established. And let me drag over the VNC. Here is VNC running through an HTTP proxy from the outside to a non-routable address. And thank you. Things will run just fine. You've owned people through HTTP. Any arbitrary protocol, any port. So yeah, this was the last of the tricks that I had to show you. I will get back, wind up the demo, and be happy to answer your questions in a little bit. Okay. Wait a second. Oh, I just ended up resetting the thing. So this was about HTTP Connect. What can go wrong with that? So just to summarize, what is it that we're really seeking when it comes to automated web security assessment? We need to overcome HTTP's customizable aspects, such as the server banner strings, response codes. But now we have technology to defeat the obscurities or anomalies with these, to improve accuracy. And these core concepts can be used to extend other assessment techniques, like proxy detection was one of them. Grouping is another one of them, and so on. So yeah, my closing thoughts, I never really discussed vulnerabilities, so there's no countermeasures. These are just things to keep in mind. This is to help us become better security practitioners. But one thing is, you can't patch or hide carelessness. Security by obscurity doesn't work. There's no patch to overcoming things like secure coding. Read good books. One of them is out there. And oops, what happened? And thank you. This is formal conclusion of what I had to say. We have around 20 minutes to take any questions and answers that you might have from this talk. Yes, please. Can we have the? Oh, we'll just keep the lights on. Yes, your question, please.
If a person were to, how much of your pattern matching, the very first part, how much of that was dependent on the HTTP RFC, and how much was dependent on the pattern by the server?
Okay. Your question is, how much of my HTTP fingerprinting technique was dependent on the HTTP RFC, and how much was it dependent on patterns that were returned? None. There is no dependency on patterns whatsoever, because I have not. This is a statistical comparator. It's just going to compare and score things. It's not looking for any patterns per se. It's just looking at overall things. It's like, how do I explain fuzzy systems? It's basically you take blocks of string, and all you care is if they differ or not. Not where they differ, or there's some quantifiable aspects like what is the degree of difference, not how many bytes differ. Say 20 bytes, 30 bytes. Like mathematically how close are two vectors to one another, how far away. That's the kind of pattern matching or string differentiation that I'm doing, not looking for anything. It could be very well applied to databases for all I care. You can use this technique to build a database fingerprinter, or whatever, SAP or ERP fingerprint. Any protocol can be fingerprinted using this technique. I just applied it to HTTP because I like HTTP. And Then again, the answer to your first part is how much of this is dependent on the HTTP RFC. Again, no dependency. All I have done is just collected a bunch of tests, requests that would typically generate varying responses. Yes, some of them may be dependent on the RFC, but in general, I never looked at the RFC to create those test requests, pretty much evolved by trial and error. And so if, say, you were to build a database fingerprinter, you could have n number of database requests and gather results and do this statistical thing. So yeah, that would be my answer to your question. Your question, please. Great question. Are these tools available? Some of the technology, especially page signatures and HTTP fingerprinting, is available in the NT Objectives Fire and Water toolkit. The toolkit's still being updated, and I will be posting out separate versions shortly. I do not know when, just as soon as I head back to India in 3 weeks and get going once again, catch up on some rest. But yes, they will be publicly available. No, the source will not be available. And no, I'm not going to talk about the internal statistic funkiness that I did. So, but you're free to use it and enjoy it and script it up and report it up and play with it and send me feedback. If it fails, I'll be happy to fix it for you. Your question. Right. Question is, I've used a training mode for building up the weight vectors for fingerprinting. Does the software go in and out of training mode and such? Yes. Well, initially the engine is the same. I just have two binaries, one to keep on accumulating and training, and then once I have, then it will show me that here are the different groups. All I have to do is go and label these groups. So I label one of the groups as IIS 4.0. Because I know that all those servers were IIS 4.0. If there's IIS 5, I label it as IIS 5. And then once I put the labels in, that is when the software becomes into production mode. I can train it as much or as little as I want. The thing just remains the same. So yeah, there's two binaries. But no, the training logic is not different than the fingerprinting logic. It's like labeled inputs and unlabeled inputs. That's what it all boils down to. Jeremiah.
How do you determine it? How do you ensure that the page signatures are the same even though there's dynamic content all the time?
How do you ensure that the page signature is the same as even though there's dynamic content? There's a lot of, I had to overcome this question with a lot of mathematical stuff. If let me give you a brief response. You familiar with Fourier transform theory? You have signals, and then if you do a Fourier transform, you group them by frequency. So if you apply this to strings, you're not looking at patterns, and then you're looking at what are the frequencies of symbols occurring in the stream, and if those are similar, then it's again, then there's a fuzzification, that what are the thresholds, how much do you do. So that's the way you could do it. The other approach I used was longest common subsequence, like pretty much what diff does. And then you have a threshold to ignore any diffs that are less than so much percentage of the string. But that's an order of n square computation. You have to, if the string is n bytes long, it'll take you an n square time to compute, and it will not scale. Somebody else had a question. Yes.
Question. The sample page you gave had a small subset section that was random.
Correct.
Have you tried it on pages that are the majority of the content is random?
Have I tried this thing on pages that majority of the content is random? Well, I would say I have not tried it on pages where 50% or more content is random, but it works with a huge, for all practical purposes, it catches high degrees of randomness. But if you have pages that are heavily random, then it won't work, perhaps. I have not tried, but you know what? If you have such a page or setup, I'll figure something out. Okay, great, no problem. Anything else? Yes, your question. Have I tried with ASP pages and different parameters passed in, tried what, page signatures with it? Yes, yes, if you have different parameters which are being passed in, yes, yes, let me actually, you know what, let me demo this. Good question. I happen to have an ASP page. It's actually a CGI page. Okay, it's this. See, here's a page, say index.cgi, page is equal to false.shtml. All right. Here's another one, page is equal to flower.shtml. So these are parameters. Now let's take the page signatures of these. So I just cut this. I will take it here. Page signature. Paste this guy. Blam, it returns something. Now let's go back to the other page. Let's say golden sunset. And page signature, paste this. Yep, the signatures are the same. So, you know, parameters can vary and signatures will remain the same. Even if there was some more or some less, as long as the basic you know, the basic program that generated these is more or less the same, it will stay the same. Have I tried fingerprinting parameters? Like, could you just explain it? I have a CGI page and I want to find out what parameters it can have. I'm not too sure how fingerprinting can help in this one. We can always, one can always look at the source and figure out if there's input fields, but no, that will happen only if there's a form. No, I don't know how to fingerprint. Or perhaps what would be the kind of value that you want to generate out of figuring out parameter fingerprints? Yeah. See, one way to do it is to, you know, if the page has parameters that are not derived from a form, then you can just crawl the site and figure out all the pages with the parameters. And, you know, once you group them by page signatures, you'll figure out that even if the parameters vary, this is still the same resource. You can eliminate 99 out of 100 and just look at the one resource. If the parameters are generated of a form, then you don't need to look at the signature, you just look at the form source code, look at the action is equal to, and figure out all the input fields that go into the form target. No, you can even have the HTML form code, right? You can have the HTML form code, you know, the form input, all those fields will be readily available to you in HTML. You don't need the source for that. And you say the action is equal to target script. All these parameters will go to the target script. Right, your question.
I'm hoping this is not a basic question, but the perception of what I see here is a proxy server, a web server that's working as a proxy server. Is that by default, or is that a special function that's running on this particular box? Again, I apologize.
No. I will answer you. Your basic question is, you know, how come a web server is, you know, what are the causes that make a web server behave like a proxy server? Sometimes, see, here is the example that I gave you was a misconfigured Squid server. It was a Squid proxy. Sometimes what happens is companies will use a Squid proxy to let their internal traffic in and out via one system. And sometimes it can be misconfigured so that it lets traffic the other way in as well. Sometimes systems like Compact Insight Manager, the way they've implemented the HTTP engine, they took HTTP proxies just by mistake and let things through. It was a design flaw. Sometimes you have a front end, say an IIS or a Netscape enterprise server, which hands over different parts of, or maps over different parts of the application to backends. So like the Netscape server, all it does is serve out static front pages. Then certain applications, like a stock trading application, might be running on an IIS system, which is internally proxied through, and the configuration is such that it's proxied through. Or a Java server plugin might be running on a different port, and things are handed off internally or rewritten. So again, these would cause this type of proxy behavior.
Okay, so it's not the web server itself, it's other things.
Yeah, it's other things, and typically the more complex something becomes, these kind of things have a higher probability of occurrence.
Thank you.
Welcome. Yeah, Apache by itself doesn't do this. IIS by itself doesn't do this. It's like, yeah, what you configure it as can leave this open. Welcome. Anything else? All right, I'm done. Thank you for your attention.